Hey, how you doing today? I'm Isaiah with Wood, Brass, and Glass. Today I'm going to be talking about the anatomy of one of my favorite parts, a roller segment. So stay tuned. On the SEG, there's these parts that rotate around the main body of the SEG, and those are called rollers. They're composed of 4 segments, and I'm going to show you today what these segments are and why they're so important for the operation of the machine. So, SEG Lab number 2, Anatomy of a Roller. This episode is going to be about the important parts of the roller, why each part is so important, and what each layer means to the whole, what each layer is comprised of, and especially the magnetic layer, which basically holds the, I like to say the software, not the magic, I could say the magic, but the software, and the rest of these pieces is the hardware. So this is number 2, Anatomy of a Roller. All right, let's begin with the innermost part, which is this neodymium. Many people get this confused with neodymium magnets. It's not neodymium magnet. It is actually the rare earth element called neodymium. It excessively loses electrons very, very fast. If you're working with the raw element, the stuff can catch on fire like thermite. So you have to have it in a vacuum chamber or an argon chamber if you're going to be doing anything with it. This is kind of the lifeblood of the machine. And this one weighs 13 grams. It's the electron reservoir. Just as a water dam has water to run the turbines, this acts as a reservoir of electrons. And my segments are going to be comprised of a rare earth mixture. And that's what John Searl talked about, and many others, that it has to be rare earth, but he used neodymium. So this is the center of the roller, weighing 13 grams. Now, this is a representation of the roller segment. This is not going to be the literal actual piece. 13 grams for this segment. All segments are the same. You don't have any that are, for the energy producing machine, you don't have any that are smaller or larger. I'm making them all identical. And next is the Teflon insulator layer. Weighs 4 grams, negatively charged. I'll be charging mine on the Van de Graaff generator I'm custom building to work for my specific purpose. So this is the second most layer, neodymium. Then you have Teflon. Now the other alternative to Teflon is nylon 6. That's the original materials John Searl used. You could comprise this out of nylon 6, which I'm going to be building an SEG version using nylon 6. One of the things I learned through doing much research with nylon 6 is that when you charge it negatively or charge it positively, the charge will soak through the entirety of the material. As we're Teflon here, the charge basically stays retained on just the surface of the material, not soaking deep into it. So nylon 6 has some interesting properties. The other thing I like about nylon 6, you can 3D print it. Teflon, forget about it. It ain't 3D print. You just get the blocks or the rods, machine it out raw. It'll be probably one of the final sections I make, because one thing I've learned about creating these negatively charged pieces, they can lose their charge kind of quick. So when all is said and done, I'll be doing these pieces are fabricated, but I'll be negatively charging them last and then assembling the entire machine together and performing tests. Again, 4 grams, the base weight, 4 grams for the right density of materials. It acts as an insulator. The rare earth fits right in between here, or right inside, of course. All right, let's move on to the next slide. All right, the really cool part I've been wanting to talk about. So, not saving the best for last, but this is the the live action part of the machine, the software, it carries the software of the machine. It is the magnetic layer. Now, with these sections I'm working with, of course, this is zinc coated, but with these products here, simply because to prevent corrosion and for aesthetics, the color, I'm getting resin coated black magnet rings. My special magnetizing machine, it will work fine with either zinc or resin, or if I want to have these gold plated, it'd do all the same. It doesn't interfere with magnetizing. So, moving on from there, starting weight is 10 grams. John Searl was emphatic that the roller have a starting weight, a specific gram to operate correctly, not just densities, but gram weight. So 10 grams on the magnetic layer, 10 grams on this magnetic layer, and you can always scale up, but you can't, from what John says, you can't scale down past 10 grams on it. Let's look at another slide that I've created to show another visual, so you can get a visual understanding of basically the software side of the magnet, which, you know, everybody interested in the SEG wants to know this. So, software side. Now, this is a representation of an oscilloscope image I got from the 1990s, and I basically had AI cleared up. But basically, the software side, reading, you have one big peak and one valley. But along this, you have 136 micro pulses. One peak, one valley, basically making 136 hertz. If anybody's paying attention, on my prior video, I talked about law of the squares. So you add all the square values up, the 16 grid 4x4 square, you get 136. So the frequency is 136. So you have one big wave, and then these micro impressions, or small little waves, going across that entire thing. So this is acting like a carrier wave, and these are submicron waves, or sub waves. All right, so for all of you curious how it would look, I used ChatGPT to construct the composite magnetic waveform on one ring segment. Basically, you would have one big peak, one valley, and then 136 embedded peaks and valleys. You have your basically your field envelope, which is your main carrier wave, and then 136 micro pulses from start to finish. That is the start of the wave to the finish. That is the circumference, full circumference of one of the roller ring magnets. So for all those techies out there wanting to know how that might look, this is a pretty good close representation. So far I've done successfully 34 hertz, or 34 peaks, micro peaks and valleys. And I've also successfully done the one peak, one valley on the main frequency of the magnet, going up and down, north and south. And then the tiny little points are basically impressions going horizontally or inside outside on the face. Okay, so this is getting to kind of the brains of the magnetic field. You have the main carrier wave that goes around the entire circumference of the ring, and then these little micro spikes. Now, one thing I learned about these magnets is very interesting. You can affect the direction on these fields. So you have your main field, you know, south and then north, south and north. And what I've learned to do, it's been very difficult, but have successfully done it, is how to make this main band move up to create the peak and valley on the main wave. So affecting it, so basically magnetizing it, or reorienting the magnetizing, so that it pushes us up, and then another section pushes it down, so creating a peak and then a valley. so that there's 4 directions on this. Basically up and down, and then out and in. And what I've been able to successfully do is that all these are basically out and in, and this one is up and down. And that's the type of magnetizing I've learned. You have to use different voltages, different techniques. It's stupidly tricky, but I have successfully done 34 pulses and gearing up eventually to do 136. But as of today, I have done 4 right in a row, 4 ring magnets that was altered the pattern here so to go 1 up and 1 down. Now, why am I doing this up and down? Well, I wasn't really sure until recently and discovered that I needed to do up and down for one reason. And that reason is, what I understand is back in the Russian SEG, they used to put sprocket magnets into this. Oh, my AI camera is working. Thank you for assisting me. Okay. I'll shut you off for a second. The reason they put radial sprocket magnets in was because they could not alter, they could not change this field pattern going up or down. They didn't know how to reorient that except for physically drilling into magnets, which I've done hundreds of these things. Annoyingly so. I learned how to do it excessively well, very well. But at the end of the day, with being able to shape these fields at will to the patterns I want, I was like, hallelujah, I don't have to put those radial magnets. And we're talking like eight layers is like 60 hours of work for one dang roller. It's a ton of work and all underwater. You know, my hand's underwater for 60 hours. It's tiresome. So the reason, one of the reasons I've learned that you need this main wave to go up and down is so that when it goes around the stator, actually, come on, little AI camera, follow me. You follow me? Hello? Okay. When it's going around the stator here, it forces that roller to rotate. Now, let me shift over and I'll show you this, not just a principle, not an idea, an actual physical roller ring magnet rotating next to the stator, the copper stator of the SEG. Okay. This is a demonstration unit that I built. It's supposed to represent the stator. No, obviously the stator doesn't move, it doesn't rotate. This does. I can control the RPM, forward, reverse, or clockwise, counterclockwise. So the reason I built this, there we go, a little bit gentler on the microphone. The reason I built this was to test rotation with the roller segments. And I accidentally discovered last summer that I could get a ring magnet, such as this, to rotate if I mechanically made it vibrate back and forth, basically, or mechanically go back and forth as it rotated. So, you know, it's like this, it's spinning, but what if you were to angle it and so it rotated it at like, you know, a wobbly wheel? Well, what happened is it would self-spin in right next to the copper spinning stator, because when a magnet moves across the surface of copper, it produces something called eddy currents. That is a magnetic repulsion. It feels like a magnetic repulsion of either direction of the magnet. North or south, it repels it either direction. Pretty cool. There's a million other YouTube videos out there showing more about what that is, but I'm not going to go all into that. Anyway, when the magnet is near to the spinning copper, it produces eddy currents. But in traditional sense, what happens is that it creates lots of drag. So how would you engineer a ring magnet to spin next to this rotating copper without creating drag? There is a way. So with this, I'll show you how it mechanically rotates. Let's zoom in real close here. Launch this up. Now normally that's what happens. No rotation. There's kind of a repulsion you can feel, and this actually twists at an angle in relation to the stator because it's causing a magnetic field to happen. But if you rotate this and it vibrates back and forth, you get rotation without touching. You'll hear a click. But as it floats across the surface, basically, those eddy currents are acting as a rotating force with the magnet. You can't hear any clicking, you can't hear any grinding because I'm not touching that stator. But the fields interacting are causing that ring magnet to rotate. Pretty cool. Now, what if there was a way you could shape that magnetic field? You could shape that magnetic field so that the magnetic field is oscillating back and forth, not the magnet. Well, let me show you this. One of the things I've been hard at work on. See if you can see the light here. I think I'm gonna have to move the camera. Hold on. Okay, that's better. Now check this out. This is magnetic viewing film. Now I've done tons and tons of, wow. You know what? Let's just pause you for a second. All right, let's take a look at this field. Now, there's lots of ways to do this, but there's only one way that I've known so far to do it right. Now, on a normal magnet, if I have one, here we go. In a normal magnet, you wouldn't be having anything interesting happening. It would just be perfectly straight. Normal magnet, okay, normal magnet, you can see the field. But in this one I've made, and 4 others, it's not just to make a squiggly line. I've done hundreds of these and make squiggly lines and they don't rotate. There is a symmetry to this that has to be very specific that I found in order to get this to rotate. Today I did probably around 30 examples. All of them came out wrong except for 4 after I changed some settings. And what this does is cause this ring magnet to rotate. Because instead of this oscillating back and forth mechanically, the magnetic field is oscillating back and forth. So let's see what happens when I do this. Now, as you can see, this continues to go as long as that stator is moving. The eddy currents are making that ring spin. I'm not clicking against the copper, try not to, but it's not the copper grinding against that magnet that's making it spin. And I can physically feel that, oh, there we go, it's spinning pretty good now. I can physically feel that eddy current rotating that and pushing against me, but it's not like it's causing drag. Like in the normal sense, a normal magnet will wow, it is really going now. That is nice. And of course, the faster it goes, wow, that is really pulling my hand. The faster it goes, okay, I gotta stop this. It's like gyroscopic effect. That's pretty awesome. I've never gotten it that fast before, so. So back to this. So if I just get a normal magnet, run it up against here, you can hear it a little bit. I can actually slow this down just a little bit, and you can see the RPM drop when I put this on. My magnetic field is causing this to drop, creating drag. Okay, let's continue on with this. because this is the most interesting part of the whole SEG, is that magnetic field. All of last year I was experimenting with a whole bunch of different designs, but it was January, I made a crazy breakthrough, which once I get it all uploaded, I'll be explaining in complete full detail on Patreon, my Patreon account. I'm explaining those specifics about magnetizing. But all that work culminated in one of the first working prototypes of my magnetizing coil. Now, it is semi-see-through, and that's because it's encased in resin to hold all the coils just right. But with my design, the ring magnet would fit inside of here and position with 2 pieces of acrylic, and then you'd hit the button on the capacitor bank, and it would form these impressions. I did tons and tons of tests and finally came up with the right type of voltage, the right current to use, to where I did around 20 different tests and every single ring came out exactly the same. It's pretty dang incredible. I also am working with making a jig that I can scan perfectly using some Gauss meters hooked up to an oscilloscope, which I'll cover in future videos. But that is coming along. And so that with a Gauss meter, just like in the prior image I showed, you'll be able to see these lines very clearly and eventually work towards making very, very clear impression lines, not just jagged and everything, as some of them are kind of right now. Let's see. I think if I can think of anything more. Let's see, I wrote some notes down. So the magnetic field, 10 grams, must weigh 10 grams, 136 hertz imprinting. Now with bigger models, say if you were to use a 5x5 square, you would have to use higher frequency. 136 hertz for me, that's difficult. I can do 34 hertz pretty easily right now. I'm gonna gear up for 68 and then move up double that to be 136. I've talked about the pole timing, the pole structure, the field timing. Now the next interesting thing is going to be how this interacts with the stator. I'm going to be doing that on another video up into somewhere in the future, because I haven't quite completed the magnetizing system on the stator. I've done the prototypes and they turn out great. But getting these fine line impressions, that's going to be a whole nother animal to conquer eventually down the road. Let's see. I think that's it for now on the magnetic. Let's move on to the copper. Actually, before jumping ahead on copper, this is another thing ChatGPT came up with. This kind of stuff that's terribly incorrect. And then it puts in like another pulse and it misses a pattern there. But just so you can get a visual on this, with the system I'm working, it doesn't have these field impressions in the inside. I don't know if that is necessary. It probably is, but I haven't quite figured out how to do that unless I mechanically put the slots. But on the outside, I have solved that for 34 hertz so far. Eventually the goal is 136, as I keep saying. So never mind this big spike here. That's not what I want. But a nice field line, and then this main carrier, it needs to go up and then back down, down and then back up. And that is what causes the rotation. So yeah, the learning curve, it's fun. Let's move on to the copper section. Yes, the beautiful copper. Now, this is not an actual real picture of one of my copper segments. This is ChatGPT. But the final and last layer of the roller segment, bingo, is the copper layer. 7 grams, starting weight 7 grams for copper. Magnetic layer 10, Teflon 4, or nylon 6, 4 grams, and then rare earth 13 grams. All those weights added together equal 34. And then the magic magnetizing frequency is 136. The copper band. The copper band, same as the stator, when in relation to a magnetic field, creates eddy currents. Now, something interesting I found when these rotate with these, the rollers rotate bare magnets, the eddy current effect is greatly enhanced, greatly enhanced. But when you have these copper sleeves on, it seems to have kind of a, I like to say not a nullifying, but a washing out effect. So another tidbit of information for magnetizing I've learned, when John Searle would do his magnetizing on his magnets, he would magnetize the magnets with the copper sleeves on them. Now today, as I was doing the alterations to create the up and down of the main wave, I found it was absolutely necessary that I had to have copper on top of this magnet while inducing current and changing the field. It didn't seem to make much of an effect, at least for the moment that I had the sleeve on it. But I'm going to be doing further tests to see if my type of magnetizing requires that or not. Okay, so that's kind of the magnetizing thing. But yeah, again, this is the emitter layer. Capture the neodymium is the electron reservoir, and then this is the emitter layer that emits the electrons out to the pickup coils, or as I'm moving on building the second and third ring, SEG, eventually on the third ring, as these rollers rotate around, the pickup coils will be picking up the electrons that come off of them. I'll be inducing high voltage, probably around between 10 and 30 kV, and so there will be, it'll be easy for the collector coils to pick up the energy that this SEG produces, if, that's the main big word, if it produces any at all. It could just be a nice spinning paperweight, for all I know. Okay, so what else can I show you guys? I don't want to just conclude the video like here. Okay, I think I got one more image I can show you all. All right, this is basically same image but different type of coloring. So I'm not sure why ChatGPT did this, but it shouldn't be like north and south and north and south. This is incorrect. But this is the full circumference of the ring magnet going completely around the whole ring, start to finish, one rotation, 136 pulses. So you have the Gauss reading goes up, and then it circles back down, or circles. It goes down and then back up to meet here. One full rotation. Now, what I'm working towards proving out, does it need to be absolutely perfectly smooth to induce rotation, like this is, or does it need to be more kind of up and then down sharply and then down? I don't know. What I'm seeing today so far with the ring samples is mine kind of go up and then down a little sharp and then flatten and then back up. So it's not a square wave or a sawtooth wave, but it's not this perfect uniform. That may just be that, I don't know. But anyway, I'm gonna leave you with that. And my next video, oh yeah, it's gonna be talking about moving into the stator section, because we covered the rollers now. We're moving into the stator section, the importance of the stator, the size in relation to the rollers. So some of my videos I'm going to have to post on Patreon for all those who want to join up with me on there, and I can give you all the fine nitty-gritty details. But yeah, be looking forward to the next video coming out in about a week. I'll be talking about the copper stator. I already have that first layer completely finished and machined to the right specs according to law of squares. So join me on the next one. I look forward to doing that for you. Again, not again. I don't know. My mind's a blank. It's late. I gotta get off this video. So you take care of yourself and join me on the next video as I go along this journey. There's so much more coming up, and I'm just trying to get everything into these videos to showcase what I've been doing, as the experiments go along, the things I'm discovering. So I'm not inventing anything, I'm just really discovering it here. Take care, have a good day.